Hello everybody, welcome to the first video in our theoretical computer science series, in which we're going to be talking about some really basic TCS concepts that you may see in some of your undergraduate classes in college. So what is theoretical computer science? According to the Wikipedia definition, theoretical computer science is a subfield of computer science and mathematics that focuses on the abstract and mathematical foundations of computation. In other words, we're combining computer science and math to analyze computer science. And so why do we want to study this? So the first main reason is we want to know what is computable and what is not computable. So more precisely, what are the bounds and limitations of computation? So as I just mentioned, is there something that we cannot compute? What are the things we can compute? And how can we tell which things we can or cannot compute? If you've taken a algorithms class or coded for a bit, you may have heard the term big O notation floated around, and that talks about how fast an algorithm can run. It can also be used to talk about how much memory or how much space something uses. And theoretical computer science also works in that department. So it talks about, is the speed of computation fast enough? So is an algorithm fast enough to compute something? Are there more efficient algorithms? And we can also ask whether what is the best possible algorithm that exists? And we can prove that nothing can be faster than something. And so that kind of falls under the bracket of how quickly can something be done. So clearly theoretical computer science has these foundational applications to tell us what is possible and what is not possible. And so in this video series, we're going to be focusing on two main things. The first one being, how do we represent objects? So we know that in a computer, everything is just a 0 and a 1, right? So our computer has to represent everything in terms of zeros and ones. So the first thing we really need to formalize is how we represent these objects. And then the bulk of this series will be focused on performing actions on those objects. And these actions are what we call the algorithms. So what are the different things that you can do to these zeros and ones and, to compute or give us certain results. And we'll see the limitations and what we can or cannot do. Okay, so with kind of the introduction out of the way, let's get into representing an object. So we will say that we have an object. We use this nice little notation for curly theta here. And we'll say what we want is we want to change this object into a string of 0 and 1s. And basically, because this string can be any length, right? We can use as much space as we want for now to represent this. We put a little star. This thing is called the clean star. And it basically just says you can choose and you can repeat this as many times as you like using these zeros and ones, okay? And so what more formally we're trying to say is we want an encoding function. We want an encoding, and we can call this encoding function E, right? That does exactly what I wrote right here. It takes in an object and it transforms it into a string of zeros or ones. Now, this encoding function does need to have some properties. And the first one is that it has to be one-to-one, right? Because we can think of a case scenario where our encoding function is not one-to-one, then we won't know what our binary string actually represents anymore. So a really important thing is our encoding function has to be one-to-one. And so how do you know if an encoding function is one-to-one? Well, we can define a decoding function. And we say we have a valid encoding if and only if there's a valid decoding. And so to write this formally, we have a decoding function D. And this function, similar to our encoding function, will take in, not instead of an object, it'll take in our 0, 1 string and transform it back into our object. And then for all objects, hopefully, so right here, we're saying for all objects, we want the following to be true. If we apply the decoding to something that is encoded, so the decoding applied to something that is encoded, we should get back the original result. right? And so this basically guarantees that our encoding function is one-to-one. Okay, so basically we have two functions, one that maps an object to 0, 1s, and another that takes 0, 1s and puts it back into an object. And if we can kind of compose these and get x back, we have a valid encoding for an object. And as an example, we can talk about the natural numbers, and something that hopefully you're familiar with is binary. And so binary is a valid encoding for the natural numbers. So we can define an encoding function that will take a natural number, put it into binary, and then define the decoding function to take binary and get back our natural number. It will be a good exercise to try and write the decoding function for this question. And so you can do that on your free time, and hopefully it'll be pretty easy to determine if your function is right or wrong. But binary is, a very common encoding function that we have that hopefully a lot of us are familiar with. All right, so there's a lot that we can do with just objects. We can manipulate objects, but more often than not, we're going to be dealing maybe with multiple objects, combining objects, doing all sorts of things. And we need to deal with a list of objects. So that kind of gets us into how do we encode lists of information. And to kind of do that, we need to define something called a prefix-free encoding. And so, as the name suggests, a prefix-free encoding will deal with the prefixes of our encoding, and it'll basically say that no two encodings will be the prefix of another. So in more simpler terms, or mathematical terms, if we have an object that maps to a string of 0 and 1s, this encoding is prefix-free. You may see me write it as PFE sometimes. Is prefix-free if for all x1 and x2 that are in our object set, we have that our encoding of x1 is not a prefix okay? And so basically, this says that our encodings are unique and that they won't be a prefix. So prefix. Above we said that binary is a valid encoding. And now I'm going to go ahead and ask whether binary is a prefix-free encoding. And hopefully you will be able to say that no, this is not prefix-free. Okay? And so that means if we have multiple natural numbers that we want to write as a list, our binary encoding, if we just string together all these 0s and 1s, won't be enough. We won't know when the numbers start or stop. Okay, so with prefix-free encodings, as you may imagine, we will very easily be able to construct lists of objects. And so if we have a prefix-free encoding, then we can construct a list of objects. And the proof for this is rather simple. It's more just through intuition, actually. So if we have a composition of objects, we can call these E1 through En. So right here we have E of x1 composed with E of x2 composed all the way with n objects. So here's the proof. We can just say that we keep reading left to right. Keep reading left to right. And when we hit a valid encoding, we chop it off and continue. And hopefully you see, because it's prefix free, we know that we're not interfering with a different encoding later on, because it's prefix free, and we'll get x1 and we can get every element uh, in this list now. Drop it off. Okay, so hopefully this all makes sense so far. We have encoding functions, which are defined based on decoding function. They have to be one-to-one. Prefix free, your encoding should not be a prefix of another encoding. And this gives us a really easy way to make lists. So this kind of is showing us that prefix-free encodings are really powerful. So maybe there should be a way to get a standard encoding and make it prefix-free. And the algorithm for that is actually pretty easy. So if we have any encoding, we'll call it E, that goes from the object to a list of 0 and 1s, what we're going to go ahead and do is every 0 turns into 2 zeros, and every 1 turns into 1, 1. Okay? And now, if we ever see a 0, 1, this will be a delimiter. And the reason we can do this is we can define a new algorithm where we read each bit by 2, right? So we're going to read 2 bits at a time. So we'll see a 0, 0, and okay, that's a 0. We'll see a 1, 1, that'll be a 1. And the second we see a 0, 1, we know that we've reached the end of one encoding and the start of the next encoding. Using steps of 2. Okay, so basically, if we go back to our original example of using binary now, you can just duplicate 0, 0, 1, 1, 1, 1, and then put a 0, 1, and then you'll know when you read it in sets of 2 that, hey, here's my first natural number, here's my second natural number, so on and so on. So this gives us a way to get a list of objects, given that an object has any encoding. We can make that encoding prefix-free using this method. So now I'm going to go ahead and ask you all the question, what would be the delimiter if we wanted a list of lists? So let's say we did the 0 to 0, 0 and the 1 to 1, 1. What would we do if we wanted a list of lists? And as a hint, you could duplicate this again and read in terms of 4, and then think about what our new delimiter would be, something that would not occur when you read in bits of 4. Okay. So with that, I think we've kind of covered the definition of prefix-free encodings, encodings, and how we're representing objects. Next time, we'll talk about a better way to do prefix-free encodings and the Huffman encoding. Thanks, y'all.